Okay, so we start in chapter 2, and this is all about symbols and terminology. So this first chunk is really just definitions and some examples of things that we're going to use. Chapter 2 is all about sets, and so you're going to learn about how to do sets and how to do set builder, and how do you define sets, and what means something is actually an element of a set. If you started at Southern in Math 20, we did sets in Math 20. So hopefully this is a refresher of sorts. But a set is simply a collection of objects. In math, generally it's a collection of numbers, but it can be a collection of anything. You could have a set of books, you can have a set of cars, you can have a set of animals. You can talk about sets in terms of anything. But each set, those objects that are within the set are known as elements. And so there's really 3 ways that we consider representing sets, and we can do it with words. We can do it with listing out all the elements, which is nice if there's only a couple elements. If there's 200 elements in a set, I don't know about you, I don't want to list all those out. And so then there's set builder notation, which allows us to represent larger sets without having to write out all the elements, which is really kind of nice. In this class, we will typically use the set builder notation to represent our elements. That's because we're going to deal with finite and infinite sets, which we will talk about in just a few minutes. But the example that's up there at the bottom, that shows you the same set listed out with words, with elements, and with the set builder notation. So, try not to mark everything off. Right here, it says the set of even counting numbers less than 10. That's telling you enough information to let you pick out a specific set of numbers or elements where it says even numbers, even counting numbers less than 10. So that would be 8, 6, 4, and 2. You can think through what those elements would be for that given set. We don't see that a ton in math. You might translate from that into the set notation. Sets always have curly brackets. You don't have to be really good at drawing them. They'll be included in the Pearson site. But the curly brackets tell you that you are dealing with a set. And then this lists out all of the numbers or all of the elements within that set. Generally, we list them in ascending order, meaning the smallest numbers are on the left, largest numbers are on the right. But you don't have to list it that way. That's usually just a good way to organize them. And you'll notice that each of the elements within that set is separated by a comma. If you don't put the comma in there, then it doesn't look like you have 2 and 4 as an element. It looks like you have 24. So we always put commas in there. And the bottom example within this example is the set builder notation, which we're going to break down here in just a minute. But this says the set of x such that x is an even counting number less than 10. So within set builder notation, a lot of times we will use words, or we will use inequalities, or we will use some form of information that lets us know what kind of elements are actually within this set. I'm going to scroll up a little bit so you can see set builder notation. Because part of learning math is really, it's kind of like learning a new language. And especially when we talk about sets, there's all these different symbols that actually stand for words and help you to explain a lot of information. And so set builder notation, we still have the curly brackets because that's telling us it's a set. But then we have an x, or if you're using a different variable, it'll be a different variable in there. If you're talking about a's or if you're talking about y's, that'll be in there. And then there's this big vertical bar right here. And that separates your variable from the kind of elements that live within your set. And so the way that we read this, if we're looking at this set builder, is the curly brackets tell us that it's a set. So it's the set of what? Well, our variable. It's the set of x. And then the vertical bar stands for such that. So it's the set of x such that, and like if we look at this one that we just looked at, it says x is an even counting number less than 10. It's the set of cars such that they're red. It's the set of books such that they're over 500 pages long. Like, that's what we're doing here. We're setting some limitations on our set so we know what kind of elements we're actually going to be looking at within that set. The X in this case represents any element that lives within that set. Again, if you chose a different variable, they would be a different variable. I'm scrolling up. I'm going to go all the way up to set builder. Sets are always indicated with capital letters. So capital A, capital B, capital C. You'll notice these top two, A and B, they list out all of the elements within them. We have 4 elements in this first one. We have 5 elements in B. For set C, though, we have 7, 8, 9, then we go ... and then we do 12. That lets us know it's following that pattern, but it's not listing out all those digits. Because if you're trying to list the set from 1 to 100, again, I don't want to list out all those numbers. That takes a long time. I would list out 1, 2, 3, ... 100. And that lets you know what it is exactly that you're dealing with within that set. Now, all of these sets, A, B, and C, they all have things in them. They have elements within them. You can have an empty set. It's also known as the null set, N-U-L-L. That means there's no elements at all. It doesn't mean zero's in there. It means there's no elements at all. So there's a 0 with a slash through it. That stands for the null set or the empty set. And I don't know why this is looking so fake. I'm going to turn this off real quick. Does that help or make it worse? I feel like we're at the eye doctor. Better, worse? 1 or 2? Like, I'm not sure which one's better. That one looks a little bit better. Okay, so 2 is better. So the 0 with the slash through it is generally the way that I will represent the null set or the empty set. Because when I write it like this, where there's nothing in it, it kind of just looks weird. And then I'm still forced to make the curly brackets, which sometimes look great. These ones look great. Sometimes they look really, really weird. So I like to do the circle with the slash through it. Pearson typically does the circle with the slash through it. Or they will type out the words null set or empty set. And then, like I said, this set where we have 0 in it does not equal the null set. 0 is a number. It is an element. Just because we use 0 to represent nothingness doesn't mean that 0 itself is nothing. So if you have a set with 0 in it, it does have an element in it. That's kind of a weird concept sometimes. Sets help us to categorize numbers and categorize different elements. They help us to see patterns in things. They help us to see relationships between numbers or between different groupings of things. So sets are pretty useful, as you will see as we progress throughout this chapter. Are we ready to flip? Okay. To flip over. We'll actually do some examples here in just a minute. Today, though, as you saw, today is titled Symbols and Terminology, so there's a lot of symbols and terminology. All right, starting right there. Feel free to look away whenever I move things. I know that can make people not feel great. So, sets must be well-defined in order to be useful. That well-defined is actually a mathematical term. There's not a great definition for it. It's better to see some examples. And so I'm showing an example of set A. Set A is A, B, C, D, ... to Z. My Z's, you'll have to get used to them. They look like that. They have a line through the middle. Back in high school, I used to make my 2's look like my Z's, and so I had to do a line through them. And my 2's changed, and my Z's never did. So those are Z's. So set A is the alphabet. is the lowercase alphabet. A, B, C, D, blah, blah, blah. So we can say and know for a fact that E, even though it's not listed right here, is actually an element of A. E lives inside this set. How do we know that? We know that because E is a letter of our alphabet. So that little funky E that's right here with the arrow pointing down says is an element of. This is shorthand in math for is an element of. And we know that because this set is well defined. We also know that theta, this is a Greek letter, theta is not an element in A. Because theta is a Greek letter, not an Arabic letter. It's not part of our alphabet, so we know it doesn't live there. Because we can know these things, we can say that this set is well defined. We know whether or not an element lives in it or doesn't. Some sets are not well defined, and you will be asked to identify whether or not a set is well defined or not. The second example, where we have set B, is the set of all good professors. That one's not really well defined, because that one is subjective. It's an opinion. Am I a good professor? Am I part of that set? I don't know. It depends on who you ask. It might depend on the day you ask somebody. Some days you guys are going to like me. Some days you probably won't. So it's debatable. And if you can debate whether or not something lives in that set, then it's not a well-defined set. So well-defined sets, you know for sure if something is in it or not, because the boundaries or the restrictions on it let you know whether or not something lives there. If it's not, like if you ask somebody for a good restaurant, how many times do you ask somebody, hey, where's someplace good to go? And then you go there and you're like, ooh, that was not good. And it's because it's subjective. It may have been great for them and not great for you. Is this movie good? Is this book good? All opinions. So those are not well-defined sets. Any questions so far? Okay. Let's actually do a couple of examples. Are we good if I scroll up to example B? All right. These are true or false, and they are giving us a element, and they're saying this element is or is not a element of the set next to it. So for A, it says 4 is an element of the set 1, 2, 5, 8, and 13. And we need to determine, is that a true statement or a false statement? False. False. 4 is not listed there. So this is a false statement.
Partially. They would not just say false.
Close-ish.
It's missing 3.
Yeah, and another one. What about B? We have 0 as an element of 0, 1, 2, 3. True. That one's in there. What about 1/5 is not an element of 1/3, 1/4, 1/6? True. So, hopefully these are straightforward. It could say, like 0 with a slash through it, so the empty set equals, and then have a set that has stuff in it, and you true or false it. Hopefully you know that that is false, because the empty set's not going to have anything in it. So some of your problems are simply identifying if something lives within your set or does not. Now, I'm going to slide up some more because the next bit's kind of long. This is why some people choose not to write down all of my notes, and they choose to just have it digitally. If you had me for Math 20, and you actually kept your Math 20 notes, this is 1.4. 1.4 was like a 5-minute lesson where I gave you guys out a worksheet, and it had all of these natural numbers, integers, rational numbers, all that definitions there. So what these are different sets of numbers, and they are they kind of grow as we go out, is the way I look at it. So the first ones are your natural numbers, or your counting numbers. This little N with a double bar in it is kind of the symbol we use for natural numbers or counting numbers. These are the ones that you learn when you learned your numbers back as a toddler. 1, 2, 3, 4, blah, blah, blah. Those are all counting numbers. You could count them on your fingers. You could count a set of items. Those are your counting numbers, and those are the smallest sets of numbers that we kind of think about, is our natural numbers. Then we go out, and we say the next ones are our whole numbers. Our whole numbers, if you look, we have 1, 2, 3, ... So it includes our counting numbers, but we added in 0. We added in a whole, like HOLE is how I kind of remember. Whole numbers have a hole in it. They're your counting numbers with the number 0. Because I don't know about you, when I start counting items, I don't ever start with 0. So that's why 0 isn't part of that, but it is part of our whole numbers. After our whole numbers, if we branch out another ring, we go out further, are our integers. Our integers, if you look at it, we start with, or we don't start with, but we have 0, 1, 2, 3, ... So we have our whole numbers, but then look, we have our negatives. -1, -2, -3. So this is like if we drew an old school number line and we put the little tick marks in it. Those are our integers. The next one gets a little bit weird. Next ones are rational numbers. Our rational numbers are any number that can be written as a fraction. That's what P over Q means. P over Q means you could write it as a fraction. If I have 0.5, that's a decimal, but I can write 0.5 as a fraction. That's half, so that's 1 over 2. So P and Q have to be integers, and we don't ever let Q be 0 because you can never divide anything by 0. 0 can live in the top part of your fraction all at once. You don't want 0 in the bottom. It always messes things up. If you're looking at decimals, though, and trying to understand if that can be written as a fraction, the way you know is if it's a terminating decimal, that means it stops. Terminating means it's done. So like 0.5, it's done. That can be written as a fraction. 0.675, that terminates. It can be written as a fraction. There's also repeating decimals. So 0.33333, where it goes off your screen on your calculator forever, that's when you took 1 divided by 3. That's a fraction. So repeating decimals mean they repeat the same number over and over and over and over again. If you were to branch out further from rational numbers, you would have your real numbers. That's anything that can be written as a decimal at all. Real numbers are like all the ones you're used to playing with. If you've had algebra classes where you've talked about complex numbers or imaginary numbers, those aren't real. Real and imaginary don't live in the same world together. They live separate. And there is another smaller subset down here at the bottom of irrational numbers. So these are ones that can't be written as a fraction. They are decimals if you type them into your calculator, but they don't end and they never repeat. So these are weird things like pi, or the square root of 5, or the square root of 2. Let me show you on the screen. I can show you what the square root of 2 does when you type it in. So if we take the square root of 2, notice it fills up my calculator screen. None of these are repeating in terms of it doesn't go like 4, 1, 4, 1, 4, 1, 4, 1. They all change. And so this is a good way to really tell whether or not you have a rational or irrational number. There's very few irrational numbers that you really have to contend with or really look at. And I list out the most common ones right here. And here's the other note for irrational numbers, because I ran out of room on my paper. Irrational numbers are neither terminating nor repeating. So I said it, but it's actually written out. So when you type in a irrational number, it'll fill it up, but it doesn't keep repeating in terms of, sorry, I'm going to cover that for a second. If I type in 1 divided by 3, so that's a fraction, this fills up my screen, But notice the 3 repeats and repeats and repeats and repeats. So this is a repeating, and so it would be a rational number. And I think the circles help communicate a little bit what these different numbers are, or what's included where. So we start in the center with the natural numbers, because that's 1, 2, 3. Then we add the whole numbers, so that's adding 0. Then we add the negatives to get to our integers. So you'll notice that if you're an integer, you're also a whole number and a natural number, because that's how these bubbles work. And you'll notice the irrationals are kind of over here in their own little bubble. They don't touch any of these because you can't be rational and irrational at the same time. So it's kind of like, if you think about, I usually use food because I'm usually hungry in this class. So there are M&Ms, then there's ones that have nuts, and there's ones that have like hazelnuts, there's ones that have peanuts, and like you can break candy down using a similar process that helps you to identify different characteristics about that information. So not all M&Ms have nuts, but all M&Ms, at least I think all M&Ms are chocolate. Like they don't have a fruity M&M yet, because those are Skittles. All right, I'm going to keep scrolling up. We are almost done. So when we talk about our sets, a lot of times we want to talk about how many things actually live in our set. Like we don't just want to know what our set is, we want to know how many elements are in there. And so if we are finding how many elements are in our set, those are our cardinal numbers, or our cardinality. Cardinal number or cardinality is the number of unique elements in a set. There's a key word in there, and the key word is unique. Some of your sets are going to have numbers show up more than once. Because if you're looking at the set of grades for this class, well, more than 2 people could have the same grade. And so that letter grade, the 90% and the 90% can show up more than once. We don't count those more than once, though, because we want unique elements. So the way we represent cardinality is we write this little N, parenthesis, and then whatever the set is. So we're going to talk about the cardinality of set A. If we were talking about the cardinality of set B, then there would be a big B in there. And so we say that is N of A. And so we will have to find the different cardinalities of given sets. Figuring out how many elements actually live in each set. Sorry, I got tilted. And I don't have a good way to block the answers, so you're just going to see the answers. So there's 5 different examples up here. They're all a little bit different, which is why I included them. The first one, we are looking at set K. Set K has the elements 3, 9, 27, and 81 in it. That's it. So when we are asked to find the cardinality of K, we can just go 1, 2, 3, 4. There's 4 elements in there. And that's it. For example, B, we're dealing with set M. Set M has just 0 in it. So the cardinality of M is just 1. There's 1 element. 0 is an element. 0 counts. If you look at C, we have set B, and this one's different because we have 1, 1, 2, 3, 2. So if I were just to count, I would say 1, 2, 3, 4, 5. But cardinality is unique elements. So I'm only going to count 1 once, and I'm only going to count 2 once. So there's 1, 2, 3 unique elements in this. So the cardinality of B is 3, not 5. There are 5 elements listed here, but there's only 3 unique. So you don't have to include repeaters. For D, we're dealing with set R, which is 7, 8, ... 15, 16. So it includes all of your whole numbers between 7 and 16. So you're 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there's 10. It will never make you do that to like 100 or anything crazy. There's 10 elements in there. They're all unique because you can see the pattern that is being followed within that set. So you know there's not going to be another 8 or another 9 in there. They're not going to try and trick you like that. And then E is kind of just right over here on the side. Just barely had room to put it up there. E says 0 with a slash. That is a set. That is the null set. The null set has nothing in it, so the cardinality of the null set is 0. Do we have any questions on finding the cardinalities and how this works? Okay. I'm going to take a drink and let you finish writing stuff down. All right, we ready to flip? Today's a little bit more definition heavy, and then we'll start doing more math with all this information next time. All right, finite versus infinite sets. Finite means there's only a limited number of it. You can count it, theoretically. It's going to have a cardinality to it. Infinite sets go on in some direction for forever. And so set A is a finite set. It has the numbers or the elements 1, 2, 3, and 4. Its cardinality is 4. There's only 4 things in it. But if we look at set B, it has 1, 3, 5, 7, and then it goes ... Those 3 dots allude to the fact that you're going to continue that pattern forever. It doesn't end like some of our other sets that we've seen where it would say ... until like 11 or 19. It goes on for forever, following that you're going to skip a number every time. And so there's actually an infinite amount of elements within that set. Because I don't care what odd number you give me, I can give you one bigger. Because that's how numbers work. There's always something bigger. And so it goes on for forever. And so that's an infinite set. So it's good to know the difference between those. You can find cardinality of finite sets. You cannot find cardinality, or I guess you can by simply saying that it's infinite. It has infinite number of elements in it. Sometimes you're going to compare 2 sets. You're going to look for equality. And so set A equals set B. And then you're like, that's a typo. It's not a typo. IFF is math for if and only if. If and only if means both of the things or all of the things that follow have to work. If one of them doesn't, then none of it works. Both of them have to work. You came to school today if and only if campus was open and you had the ability to come to school. If one of those things didn't work, you wouldn't have been here. So they both had to work together to get here. So set A equals set B if and only if every element in A is also an element in B, and every element in B is also an element in A. So you have to be in both things. That's the only way for these 2 sets to be equal. If one element lives in one of those sets and not in both, those 2 sets are not equal. We've got 2 examples of set equality. Example 1 says A is set 101533 and B is set 0135. Are those equal? Yes. Yes. They are equal. Now, in set A, we represent numbers 1 and 3 more than once, but is there anything that lives in A that doesn't live in B? No. Is there anything that lives in B that doesn't live in A? No. So these are equal. Repeaters don't mess it up, so that's good. So then if we're looking at example number 2 for set C and D, what do you think? Is C equal to D? The question to ask is there anything living in one of them that doesn't live in both? 0. Yeah, 0 lives down here in D, but there's no 0 living up here in C, so these are not equal.